Hi everyone, this video covers homework 10. It's 8 problems from chapter 13, which is all about gravity. Um, I think you're going to find most of these problems are pretty easy, but there's a few that are very hard, and I wanted to create this video to help you get through those. Um, so once you're done with this, you should know everything I want you to know from chapter 13. So let's start with our equations. And these are the equations we learned from chapter 13. The force of gravity between any two masses is G times M1 times M2 over the distance between R1 and R2. If we note that for M2, G M1 M2 over R12 squared, this gives that the acceleration of gravity is G M1 over R12 squared. Okay, and similarly, you could write M1A is that, which will give you A is G M2 over R squared. Equal and opposite forces. The force is the same for each of them. The acceleration is different for each mass, usually, unless they were equal. Okay, then we learned Kepler's laws. In Kepler's laws, we had for a elliptical orbit, where A, and there was the perihelion and the aphelion, and at the foci was the big M. Big M is at the foci, little m is what is rotating around. This is EA, this is RP, this is RA. From all that, we get that 2 times A, which is the semi-major axis, is RP plus RA. It's the distance from big M to the closest approach and the distance to the furthest approach. And since the semi-major axis is A for each of them, it's 2A. Further from this, you can see that RP has to be equal to A minus EA, and RA is A plus EA, right? And that's it for basically Kepler's first law. His second law told us that the aphelion radius times the velocity tangential at aphelion is equal to RP times VP. If we can assume that V is R omega, then we get that RA times omega at A, the angular velocity at A, is equal to RP times the angular velocity at P, or RA squared is omega A, or times omega A is equal to RP squared times omega P. The final one of Kepler's laws told us that T squared was equal to 4 pi squared over G times whatever big M is, whatever you're rotating around, times the semi-major axis cubed. And if we're in the solar system, T squared is equal to A to the cubed, as long as this is in Earth years and this is in AU. The last thing we need to talk about is energy. And potential energy is similar to MGH, is minus G, whatever you're rotating around, times your mass divided by the distance between them. The kinetic energy is mv squared over 2, which is equal to G times whatever you're rotating around times your mass divided by 2R. And if we say that the total energy is potential energy plus kinetic, we would get GMM over 2R minus GMM over R, which gives us minus GMM over 2R, or 2 times the potential energy. That's where we're going to have a problem in like the 7th question that we do. But yeah, and the last thing that we should note, if necessary, is G is 6.673 times 10 to the minus 11 Newton meter squared over kilogram squared, and 1 AU is 1.5 times 10 to the 8th meters. Let me make sure of that. 1 AU is 1.5 times 10 to the 11th. Yeah, I had a feeling I had that wrong. Okay, so we're all good. It looks like a lot, but it's actually not that much to remember. Once you've done a few of these, they're pretty easy. And let's get started. So problem 1, problem 13.3, asks us to find the separation between a 3.4 kilogram particle and a 4.4 kilogram particle for their gravitational attraction to have a magnitude of 6.2 times 10 to the minus 12 newtons. So first of all, what are they giving us? That's always our first step in any of these problems. We need to look at what they are specifically giving us. Okay, so what are each of these quantities here? This would be, mass 1 is 3.4 kilograms. Mass 2 is 4.4 kilograms, if we need it. The gravitational attraction, what that is saying is the force of gravity is 6.2 times 10 to the minus 12 newtons. And what they're asking us for is what must the separation be? So they want R. And we know the force of gravity is G times M times M1 times M2 over R squared, where R is the distance between them, okay? So we want to solve this for R, and we see quite easily that R is the square root of G M1 M2 over the force of gravity given. And if we plug numbers in, I'm not going to plug numbers in. You can easily compute that. This is 6.67 times 10 to the minus 11, 3.4, 4.4 divided by 6.2 times 10 to the minus 12. As a really quick check though, if this is 10 to the minus 11 and this is 10 to the minus 12, this is going to give us something times 10 to the 10th. So just remember that. Otherwise, this problem's super easy. It's just a little practice on using the equation for Newton's universal gravity, okay, between any two objects. All right, moving on. Miniature black holes. Left over from the Big Bang beginning of the universe, tiny black holes might still wander the universe. And if one had a mass of 1 times 10 to the 11th kilograms and a radius of only 4 times 10 to the minus 16 meters, which is extremely small, smaller than atoms. Atoms are generally on the order of 10 to the minus 9. So this is ridiculously small. Reached Earth, at what distance from your head would its would its gravitational pull on you match that of the Earth? And we're going to assume G is 9.83, okay? So let's draw a little picture. We know that if you're standing on the surface of the Earth, at some radius of the Earth, the gravitational force is M times G, where G is 9.83. What we want to know is if we put this black hole somewhere, some RB away, right? I shouldn't draw that way though, because actually it's going to pull you toward it. And we want to know what RB is, how far away from that you would be to feel the same gravitational acceleration. So we want that the force on you, MA, due to the black hole. So the force due to the black hole is MA, your mass times A. And that is going to be G times mass of the black hole, right, times your mass over the distance to the black hole squared from your center mass to the black hole squared. If you cancel these off, you get that A for the black hole will be G, mass of the black hole, over R black hole squared. If we assume, though, that A has to equal G, so we're assuming that A will be the same for the black hole and for Earth, so there's no net gravitational force on you. So if we assume this is 9.83 meters squared, or meters per second squared, we can find RB as the square root of G times the mass of the black hole over A, or little g if you want. Not too hard to do. Again, plug in for G 6.673 times 10 to the minus 11 kilogram, Newton meter squared over kilogram squared, times this mass of the black hole, 1 times 10 to the 11 kilograms, divided by 9.83 meters per second squared. Take the square root, and you'll get an answer. That's not too difficult to understand. It's almost exactly the same problem as we just did, although in this problem, you have to know that you're assuming the acceleration due to the force of gravity of the black hole is equal to the acceleration of the Earth at the surface. Okay. Not too hard, pretty easy. Let's move on. Something a little bit more fun. We are now going to be using, for the next 3, Kepler's equations. So the first 2 problems were all just universal gravity, the law of universal gravity by Newton, and figuring out the distance between objects, where that force, or what that force is for the distance between objects. Now we're going to switch over and use Kepler's laws. Okay. So in problem 13.49, we're told that in 1596 AD, Chinese astronomers spotted a comet, and then essentially almost 1400 years later, they spotted it again in 1961. Assuming the time between the observations is the period of the comet, and we take its eccentricity to be to almost 1, what are the semi-major axis and what is the greatest distance? So we are given that the time in years, Earth years, is 1961 minus 596. That is 1,365 years, Earth years. Okay, we'll talk about that in a minute. We're told that the eccentricity is nearly 1. And we're asked to find A, where A here is the semi-major axis of the orbit. And we're also told to find the greatest distance from the sun, which is the aphelion distance. Remember, the perihelion is when it's very close, and the aphelion is where it's very far away from whatever mass it's rotating around in the elliptical orbit. All right. This problem you could make a little complicated, and you shouldn't, which is why I gave it to you. And it's also kind of the quiz problem that we got this week. Remember that we can find A from t squared is equal to 4 pi squared over gm a cubed. And that means that A is the cube root of 4 pi squared. Sorry, I'm losing my mind. Is G mass of the sun times the period squared over 4 pi squared. Remember that the m in this equation is what the object is rotating around, and the object in this problem is a comet orbiting around the sun, not the Earth. Okay, you could do all that, but for objects in our solar system, it turns out that 4 pi squared g over m, if you convert it into Earth years, time in Earth years over meters in AU, that this constant becomes 1. And so what we get is, as long as T is in Earth years and A is in AU, we can find just this, which is really simple. So A here is the third root of 1,365 Earth years. I get for that, if I hit my math button on my TI-83, I can go to the cube root of 1365, and I get 11.09 Earth years. Or I'm sorry, 11.9 AU. So let me get rid of that. So this is times AU cubed. So these become AU, and I get 11.093. So 11.093 AU, if I want to convert back to meters, which is what Wiley Plus actually asked me for, I can just divide, or I can just do my unit analysis, 1.5 times 10 to the 11th meters, and that is pretty simple to see. What I get is 1.66 times 10 to the 12th meters is A. Okay, 1.66 times 10 to the 12th meters is my A. Not too bad. Then, in order to find RA, I know A and I know E, and RA is, RA, if we go back and look, is A plus EA. And therefore, this is A times 1 plus E, and 1 plus E is 1.989. So this is about 2 times that, which is somewhere around like 3.15 times 10 to the, or 3.2 times 10 to the 12th. Not too hard to do. Pretty easy, in fact. Again, you could have put in the gravitational constant here, 6.673 times 10 to the minus 11. You could have put in the mass of the sun as basically 2 times 10 to the 30th, and put in for the period, you could have multiplied this by pi times 10 to the 7th seconds per year. There's about 3.15 times 10 to the 7 seconds in a year. You could have done all that, but you didn't need to if you remembered that for our solar system, T squared is equal to A cubed. That only works in our solar system because of the value of the sun that you're rotating around. If you were in a different solar system, the mass would be different, this mass here. But otherwise, this isn't too hard. It's more a test to make sure that you understand what your variables are and you can find them. And so that we can talk about this T squared is equal to A cubed in our solar system. Okay? All right, let's move on. A satellite in an elliptical orbit, we don't know where this satellite is, by the way. It could be anywhere. It could be in the Andromeda galaxy. We don't know. But a satellite is in an elliptical orbit with a period of 7.79 times 10 to the 4th seconds, about a planet with a mass of 5.8 times 10 to the 24 kilograms. And at aphelion, it has a radius of 5.9 times 10 to the 7th, and its angular speed at that point is 7.4 times 10 to the minus 5. And this is what we want. So as I said before, our first job here is to write down what we know. So we know the period as 7.79. And we know the mass of what it's rotating around, big M, 5.8 times 10 to the 24th. We know at aphelion, the aphelion distance, RA, is 5.9 times 10 to the 7th meters. And finally, we know that VA is 7.415 times 10 to the minus 5 rad per second. Okay? I'm sorry, we know that omega A. You gotta be careful with that. Omega and V, it's easy to confuse what they're asking for, but then you can find it later. We're gonna assume that V is equal to R omega at aphelion. This would be RA omega A and RP omega P for VP. Okay, so we need to find the angular speed omega p. And we know from Kepler's third law that RA squared is omega A is RP squared omega p. So the first thing we need here is we need to be able to find RP. We have RA, it was given to us. We have omega A, that was given to us, but we don't have RP. So how do we find RP? Knowing only RA, M, and T. Well, let's work backwards a little bit. We know that RP is equal to 2A is equal to RP plus RA. So 2A minus RA will give us RP. And then in this, we better find A. And A we can find by T squared is 4 pi squared G over M A cubed. And we know T and we know big M. We can't assume this is 1 if this is in years and this is AU because we're not necessarily in our solar system. This M is totally different than the sun. Actually, I should say even in our solar system, if you're rotating around the Earth, you can't assume this is 1. That only works when this is the mass of the sun, okay? So from all that, our first job is find A, use A to find RP, use RP to find WP. So let's do that again here. So we know that T squared is 4 pi squared over GM A cubed. From that, A is the cube root of T squared G times M of the mass divided by 4 pi squared. Once you get that, 2A is RP plus RA. And you want RP here. So plug in 2A minus RA. I'm going to come back and highlight stuff that you know in a minute. And then knowing that RA squared omega squared at A is RP squared omega P, we can get omega P is RA over RP, square it, and multiply by omega A. We were given T, M, RA, and omega A. So we were given T, we know G, we know M, we know 4 pi squared, obviously. Once we find A, we'll have A. We were also given RA, right? And so here we can find RP, and then we were also given omega A. So find RA using this equation, which you're going to need A using that equation, and you'll get there. This problem is all about Kepler's laws and the equations associated with them, because basically each step, step 1 here, is using his third law that tells you that the period squared is equal or approximately the semi-major axis cubed. For the second part of the problem, you would need to use Kepler's first law that says that orbits are ellipses, and therefore this is an equation from an ellipse with the sun or whatever you're orbiting around at one foci. And lastly, you're going to use his second law, which is equal area, equal time. But as Newton showed, that is equivalent to conservation of angular momentum, where if we multiplied this by m, and I'm so sorry, there should be another. If we multiplied this by m, we would get the angular momentum. Because remember that mr squared is for a point particle I. So this would be I omega, which happens to be the angular momentum. And if we convert this omega into v over r, we get that this is mv times r. And that is also the angular momentum. So this is just saying that angular momentum conserved and equal at the aphelion and the perihelion, which was equal area, equal time in Kepler's laws. All good? I don't think this one's too hard, but on a higher level of learning, understand that what you're supposed to get out of this is how to apply each of Kepler's 3 laws as equations, okay? Lastly, The orbit of the Earth around the sun is almost circular. We're not going to assume it's circular, but it is almost circular. And the closest and furthest distance are given as these. So the perihelion distance of Earth is 1.47 times 10 to the 8th kilometers. Okay, so that's 1.47 times 10 to the 11th meters. And RA is 1.52 times 10 to the 8th kilometers, again, 10 to the 11th meters. And so we want to determine the variation between perihelion and aphelion of the total energy, the gravitational potential energy, the kinetic energy, and the orbital speed. And this is really understanding the energy of orbits. That's all it is. So it's understanding that the gravitational potential energy at any point is minus g m m over r. And the kinetic energy at any point is g m m over 2r with a positive sign. And further, the energy is equal to the kinetic energy plus the potential energy. So the total energy at RA and at RP, the energy at A at any point has to be equal to G M M over 2A. And by conservation of energy, that says that these energies, okay, have to be equal to the kinetic energy at P plus the potential energy at P, and that has to be equal to the kinetic energy at A plus the potential energy at A. Okay, this is not equal to GMM over 2P. That's where I kind of got a little weird. I was tired when I was doing that part of the lecture. This does not equal GMM over 2P. In fact, what it equals is GMM over 2P minus GMM over P, RP. I guess 2RP. Okay, and this is equal to GMM over 2RA minus GMM over RA. Okay, and yeah, if you do that, I guess they do equal, which makes this a little wonky. We talked about that before. It's always an issue. Don't try and set them equal to each other. In fact, maybe what would be better is to write this as mvp squared over 2 minus gmm over rp is equal to mva squared over 2 minus gmm over ra. It's messy, but assuming that the energy is the same, what is the change of energy from A to P, right? So that's just the energy A minus the energy P, but since they're equal, it's 0. By conservation of energy, you know that answer A is 0. All right. So what is the change in potential, or the change in potential energy? So the change in potential energy, and by this we want the difference of potential energy as a magnitude. So let's do this. The potential energy at aphelion minus the potential energy at perihelion, okay, minus and a minus. So this becomes GMM times 1 over RP minus 1 over RA. Note that in this case, what we should see is we're going to get something negative because RA is bigger than RP, right? We're going to have a negative difference in potential energy, but take it as the absolute magnitude, okay? And remember that the problem is the Earth and the Sun, so GMM is G times the mass of the Sun times the mass of the Earth, right? The mass of the Earth, 5.97 times 10 to the 24th kilograms. Mass of the Sun is 1.99 times 10 to the 30th. You can look those up on the internet, in your book, wherever you want. Your book sometimes, and Wiley Plus, I think, sometimes uses 5.98. If you're having a little bit of trouble and it's telling you that it's wrong, it might be because of that. All right. Now, what is the change in kinetic energy? So the change in kinetic energy, we know that the change in energy is the change in kinetic energy plus the change in potential energy, right? And this is 0. So the change in kinetic energy better equal the change in potential energy. Same answer as part B. You don't need to do anything. You could figure it out by using GMM over 2RA minus GMM over 2RP, but you don't need to. You can use this fact that the change in energy is 0 and the change in kinetic energy is equal to the change in potential. That's pretty easy to understand. And then finally, and this is the last one, it wants the difference in kinetic energy. So it wants the change in kinetic energy. VA minus VP. Now, there's a couple ways we could do this. I would say that the easier way, you're given RA and RP, right? And I'm trying to figure out what, oh, yeah. So one way to do this, change in B, is, and I need a new slide for this. So one way to do this is to say that we know that the change in kinetic energy was the change in potential energy. And we know that the change in kinetic energy is MVA squared over 2 minus MVP squared over 2. We know this is a number that we found here. This was some number. Okay, so whatever that number is delta KE here. Second, we know from RA, VA is equal to RP, VP, we know that VP is RA, VA over RP. So this is MVA squared over 2 minus MVA squared over 2 times RA over RP squared. That's Newton's second law, angular rotation again. All right, sorry, Kepler's second law, done by Newton. Okay, so from this, we can solve this for VA by using VA is the change in kinetic energy times 2. So let me write this right here. This is M over 2 times VA times 1 minus RA over RP squared. And this is the change in kinetic energy. So this is 2 times the kinetic energy divided by the mass times 1 over 1 minus RA over RP squared, and take the square root of this whole thing, okay? And if you do all that, you should find it somewhere around 2.95 times 10 to the 4th meter per second. And then the last part that you need to do is remember it wants the variation between the two. So if we want the variation, we want VA minus VP. VP. So we want delta V. And we know that, as we've already said, that VP is equal to RA over VA times VA. Man, I am not able to talk today. Sorry, everybody. So delta V is VA times 1 minus RA over RP. And that should be pretty small. Remember that RA is only slightly bigger than RP. So this is going to be some negative, very small negative number. Essentially going to be 1 minus, I can do it right now. Going to be 1 minus 1.52 divided by 1.47. Yeah, so about 0.03 times. So this ends up being about VA times 0.034 or something with a negative sign. You're going to get a negative number. If I multiply that by 2.95 times 10 to the 4th, I get about 1 times 10 to the 3rd, which is fine. Just a bunch of math on that one. Nothing major. Just a bit of a pain. Okay. All right. Let's move on. An object lying on the planet's equator. It's accelerated toward, it's accelerated number 1. So when an object is going around a planet, let's call it a box, okay? It's got a radial acceleration, ARAD. Remember that is V squared over R. And it's got a period here of 2.1 days. And then, because the planet is rotating around some star, let's say it's the Earth, is rotating around some star, it also has an ARAD of V squared, but for the planet this time, over R. Right? And the period of the planet around the star is 2.1 years. And then finally, that star is rotating around the galaxy. So this some point at the center of the galaxy, it also has an ARAD of V of the star over R squared, V squared over R. And it's got a period of 1.4, sorry. It's got a period of 1.5 times 10 to the 8th years, okay? And then it gives you the radiuses of each orbit, and it asks you to calculate the magnitude of the acceleration for each of these by, and then divide that by g. So let's see that for 2 of them. I'll let you do the last one. So if you know the period in days, so 2.1 days, remember that you want to turn this into seconds. There are 86,400 seconds in 1 day. So that's going to give you some big number. Now, once you have the period, right, you know that omega, we're trying to find a rad is v squared over r, but if v is equal to r omega, then this becomes r squared omega over r, and that becomes r omega squared. So we're trying to compute a is equal to r omega squared. Now t is equal to 2 pi over omega, or omega is equal to 2 pi over t. So if you take 2 pi and divide it by, in this case, 2.1 times 86,400, you'll get omega. And then if you multiply that by r, so in the first case, we were told that the radius of the planet is 5.6 times 10 to the 6 meters. So if we multiply that by the radius of the planet, so this is the radius of the planet times omega of the object squared, and we get a. Divide that whole thing, whatever you get for a, divide by 9.81 meters per second per g, okay? And that'll give you, second squared, that'll give you g. So let's do this really fast. Using the fact that r is 5.6 times 10 to the 6, 5.6 times 10 to the 6 meters, I can find that omega is 2 times pi divided by 2.1 times 86,400, and that gives me that omega is 3.463 times 10 to the minus 5 rad per second, okay? And if RP is that, then this becomes 5.6 times 3.463 squared times 10 to the 6 times 10 to the minus 5 times 10 to the minus 5 is 10 to the minus 4. Okay, so 5.6 times 3.463 times 3.463, that gives me 67.157 times 10 to the minus 4, or about 6.72 times 10 to the minus 3 meters per second squared. But I want this in terms of g. So if I divide this by 9.81 meters per second squared per g, where g is just a unit here, I get 6.72 divided by 9.81. I get 0.685 g. 0.685 g's, right? Times 10 to the minus 3, sorry. Yeah, almost forgot that, sorry. 10 to the minus 3 g's, right? Very small. For the other two parts, same deal. You need to use, for 1 year, there are 3.15 times 10 to the 7 seconds. You could multiply 60 seconds times 60 minutes times 24 hours times 365 and a quarter days, but this is what you'll get, which is equivalent to pi times 10 to the 7 seconds per year, okay? It's a common shortcut in astronomy, just use pi if you need the amount of time in a year. And you're given the r's, so it's just repeating the same calculation over and over again, dividing by g so that you can kind of compare them to the gravity on Earth. They'll all be pretty small. The effect of rotating around the Earth is very small compared to the gravity toward the center of the Earth. The gravity due to rotating around the sun is even smaller. Gravity rotating around the galaxy is even smaller. Not a huge deal. I actually thought this was more interesting than probably useful, but it is practicing a question. I'm going to skip to the final problem first and then come back to problem 7. So the final problem, we're told that the gravitational, or the escape speed from a spherical asteroid with a radius of 937 kilometers and a gravitational attraction of 1.44 meters per second squared, that we want the escape speed. And if an object does escape with a initial velocity of 1,380 meters per second. How far away will it get before it's stopped by the gravity of the asteroid? And then what speed will it hit if it drops from a certain distance above the surface? First things first, what did they give us? They gave us 937 kilometers in radius. So the radius of the asteroid is 937 times 10 to the third meters, okay? And A at the surface, right, is 1.44 meters per second squared. However, this isn't useful yet. We need to make it something useful. And let's look at this. At the surface, MA is equal to GM little m over r squared. If I cancel the m's and I multiply through by r squared, I see that this is true. And AR squared, which is equal to GM, well, I'm going to leave that alone for a minute. So keep that in mind. Everywhere in my problem that I have GM, I can substitute AR squared. That's pretty useful. Okay. Now, we want the escape speed. And if you don't remember, the escape velocity is the velocity when mv squared minus gmm over r squared is equal to 0. It's the, effectively, when you get really far away, there's no potential energy and there's no kinetic energy, and that's equal to the initial velocity, which is also called the escape velocity. If I move this over and I cancel my m's, I see quite easily that my initial velocity has to be equal to square root of 2gm over r squared. I'm sorry, I knew that was wrong. Over r. Potential energy is over r. Okay. So we have that all good. We can quite easily see here that if we plug in for GM, AR squared over R, right? Then the R's go away. Well, one R goes away. And we get 2AR, which is 2 times 1.4 times 937 times 10 to the third. You can do that yourself, but that's the escape speed. It's the speed when initially it has some velocity and some potential energy, and then it gets very far away and the velocity becomes 0 and the potential energy becomes 0. So we got that. That's part A. Part B, we want to know how far away it will get if it leaves with an escape speed of 1380. So if V initial is 1380, and here things get a little tougher. We're going to have to use energy. So what is the energy at the surface? So the energy at the surface, right, is mv naught squared over 2 minus gm over r at the surface. But when it gets very far away, it has to lose all of its kinetic energy. So all of its kinetic energy has to become 0, and it can only have some potential energy. And that potential energy will be GM over R plus some height, right? This is the final. This is the energy at some radius plus some, I'm going to call it h for height, but basically we start here, it shoots off, and eventually it gets somewhere at r plus h, where it's got no more kinetic energy, okay? We want to know what this r is, and that's a little difficult. So let's start off by, we want to know what this h is, I'm sorry. So we start off by getting rid of m, all these m's, okay? And we're also going to put AR squared in for GM. So we see that we get V naught squared over 2 minus A R squared over R is equal to minus A R squared over R plus H. Now we could get rid of that and just write it as A over R. We want. It makes it a little bit easier. Doing the real quick math, if I multiply both sides by R plus H, okay, that goes away here. And if I move this stuff over, what I get, I'm going to go to a new page. So what I get here is I get R plus H is equal to AR squared with a minus sign divided by V naught squared minus AR over 2 minus AR, but that negative sign I can move through. So I get AR squared over AR minus V naught squared over 2. Okay, if I then move this R to the opposite side, I can get a minus R. And this is my H. Sorry. This is my H. Okay. So let me just kind of erase. Right. Pretty easy to see. Going back a second, remember that we found the energy initial, and then we found the energy when KE went to 0, when the kinetic energy went to 0. That's as far away as it could get. At that point, it's still going to have potential energy, and it's going to have that potential energy when it is R plus H away, okay? All right. So the last thing is, with what speed will the object hit the asteroid if it's dropped from 799.7 kilometers above the surface? And here, what we need to do, so I'm going to do a new slide. So at 799.7 kilometers, we want to know what speed will it hit the Earth at. And you might start thinking, oh, I need to do some constant acceleration. Can you do constant acceleration? No. The acceleration is not constant. It varies based on the radius. So we can use energy, though, and we can basically undo what we did in part B. So we're going to assume that it drops from 79.7 kilometers above the surface. We're going to assume at that point that it has no velocity. So the energy at 799.7 times 10 to the third meters, and the energy at the surface, we need to set those two things equal and solve for V at the surface, okay? We know that V, let's call this initial. V initial has to be 0. So it has no kinetic energy. It only has GM M over R plus 799.7 times 10 to the third meters. Okay, that's how high it is above R. It's at R plus 799.7 times 10 to the third meters, right? It's not at 799.7. It's at R plus that. The final is M V squared over V final, I guess, over 2 minus GM M over R of the surface. And so we want to find V final here. Again, all these little masses go away, and we see that V final squared over 2 is equal to GM times 1 over R minus 1 over R plus 7.99 times 799.7 times 10 to the third meters. okay? If I multiply through by 2, I can get rid of this. And if I take the square root of all this, that's pretty easy. I can get a number. We were given the radius of the asteroid was 937 kilometers, or 937 times 10 to the third. So that part's not too hard to understand, right? And we're all good, I hope. The key here is that the energy is conserved, and therefore you can use conservation of energy to figure out what the speed of the object is. This problem is really only in a vertical plane. We're going to talk in a minute about something that's actually rotating, but this object is being pulled closer or further away from the surface of the planet. And V final is actually in the direction of the planet. It's not rotating around. It's being gravitationally attracted, but it's not orbiting. This object is not orbiting. When you escape, you're not talking about orbit, you're talking about escape velocity away from the center of mass, okay? Now we're going to talk about something that is orbiting, and there are going to be all kinds of issues. So this, I believe, is the hard problem of this homework. That last problem was kind of hard because of the R plus H, but this problem I definitely think is the hardest problem. It's a pain, and it's probably the reason why I really wanted to go through the homework solutions with you all. Okay, so we're just talking about a satellite. And at what height above the Earth's surface is the energy required to lift a satellite to the height equal to the kinetic energy required for the satellite to be in orbit at that height, which is a horrible, horrible mouthful. So at what height above the Earth's surface, we should write that, but is the energy required to lift a satellite to that height equal to the kinetic energy required for the satellite to be in orbit? And then for greater heights, we have this other question to answer. But for now, what they're asking us is, we know that when a satellite is moved off the surface of the Earth, we must put some energy in, and we'll talk about that, to get it up there. And then, in order for it to rotate, it's going to have kinetic energy. So we need to do some potential energy work against gravity, and we need to put it or give it some energy so that it will have some kinetic energy. So the energy has to be equal to the kinetic energy that we have to give it, plus the change in potential energy that we have to give it. So the change in kinetic energy, I should really say. But the energy has to be the amount of energy we put in for kinetic energy and the amount of energy we put in for potential energy. We're going to talk about what those things are. And it's not as easy as it seems. So please, if you're kind of half paying attention and have this on, really pay attention to this one. This one's super important. Okay. And we want to know at what height is the kinetic energy and the potential energy equal? Okay. So first of all, the kinetic energy is not too bad. The change in kinetic energy, if mv squared, is simply the change in kinetic energy is mv final squared over 2 minus mv initial squared over 2, but v initial, we're going to assume, was 0. So we have to put in energy equal to mv final squared over 2. But this kinetic energy is also equal to m over 2 times r plus some height. Because initially we were at r, and now we're at r plus h. And indeed, our goal is going to be to find this h once we have everything set up. But that's easy to understand. You put energy into the system in order for it to rotate around in a circle. You give it some energy with kinetic energy. However, there is now a change in potential energy that we have to account for. And in fact, this is why this problem is so hard. If we were moving closer to the center of the Earth, would gravity be doing positive or negative work? So remember, the work done is F dot D, and gravity is down, let's say. So the force of gravity is down. And if we go along with the force of gravity, then we actually convert, we let gravity do the work of potential energy, okay? The work is being done by gravity, and it's positive. When we go out, we have to do negative work against gravity, right? Because our displacement, I should write the displacements down. When it's falling with gravity, gravity is converting potential energy of gravity into kinetic energy. Here, we're having to fight gravity to push it further out, which means we have to put energy in to the problem. We're going to see that we get a negative potential energy change. The potential energy here at the surface is greater than the potential energy out there, right? But is that the work we do against energy? No. The work we do against gravity is basically equal to the negative of the potential energy change, okay? Which is really weird. So let's talk about that for really fast. Potential energy is G M M over R with a negative sign. That's the potential energy of gravity when we're talking about orbits. And if we want the change of potential energy, when we move from some close radius to some far radius, minus G M M over R plus H, right? But this is a minus minus. So this is really G M M 1 over R plus H minus 1 over R, okay? So that is the change in potential energy. Actually, I have that backwards, I'm sorry. Let me fix that really fast. So I want final minus initial. This is final is R plus H over R, so R plus H, okay? Now note that, and I should say that this, I'm just gonna erase all this and rewrite it. This is G M M times 1 over R minus 1 over R plus H, and this gets multiplied by GM over GMM. Okay, and we can see that because R plus H is going to be bigger than R, this is going to give us some positive work, okay? Some positive energy. That's what we want, okay? This is the energy that we have to put in to the orbit to move it out there. So the change in potential energy is the work that we have to do against gravity to move it out there. That's kind of difficult to understand. The signs get all messy, and yeah, so that is the work. But, and this is where things get weird, okay? So the change in potential energy from final to initial, we have to actually do that as negative work. Now, why? What does that even mean? So the energy that it had at R was negative G M M over R. And the potential energy it has at R plus H is negative G M M over R plus H, right? So basically, as it moved out, we gained energy, right? This is definitely less than this. So we gained energy in the system. That doesn't make any sense. We have to have a negative sign on here. So the change in potential energy, the work done by us on satellite, is equal to the negative of the change in potential energy, which is the negative of this, which is G M M times 1 over R plus H minus 1 over R. Remember, here, E at R is less than E at R plus H. And therefore, I'm sorry, that's backwards. And therefore, what that's saying is by moving it out, we would gain energy? No. We have to do work against gravity. So we have to put energy into the system is how you have to see this. And that's what I'm kind of stumbling over. I'm trying to get through your head that when you move something away from another mass, you have to do work on it. It's going to cost you energy. So the energy has to be the negative of the change in the potential energy, okay? That's the work that you would have to put in. I hope that makes sense. I'm going to try and explain it one more time slowly. So we start off with an object here, and it has some potential energy of Gmm over R, because it's at R. And then I pull it away from there to a point where this is R plus H. And when I've done that, I've had to do work against gravity, and that work is F dot D, where D is R plus H, right? Minus R. So this H, so I have to do the force of gravity times H with a negative sign. So I have to do negative work. Therefore, I'm taking energy out of the system, right, as I move. But that means I have to actually fight gravity. I have to put energy in to make it go further away, which is why the signs are such a mess. So what we say is we say that the change in potential energy, which is the potential energy final minus the potential energy initial, is Gmm with a minus sign over R plus H minus a minus, which is plus Gmm over R. But this, the work we do, has to be the negative of this, okay? And because it's the negative of this, we get this. That's long-winded, but I hope it makes sense to you. You have to supply some energy to move it further away. Because the potential energy is actually decreasing. But the potential energy is negative, which is a mess. I told you it was a mess, and it is a mess. So let's see if we can make some sense of the whole problem, and we're going to come back to this. So we want to know the energy required to move it from R to R plus H, and to change its V from 0 V is equal to 0 to V is mv squared over 2 is equal to 0 to mv squared over 2 is equal to Gmm over 2R plus H. Okay. So we need the energy to move it from R to R plus H, the potential energy, and this. So that is the change in kinetic energy plus the change in potential energy. Now the change in kinetic energy is, and these have to be equal. So the change in kinetic energy has to equal the change in potential energy. That's what it's stated in the problem. We want to know what is H. What is H when the change in kinetic energy is equal to the change in potential energy? And the change in kinetic energy is mv final squared over 2 minus mv initial. V final squared over 2 minus mv initial squared over 2. And the change in potential energy we're going to write as Gmm over R plus H minus Gmm GM over R, but remember that these are minuses and plus, okay? Therefore, remembering that this is 0, right? So we get MV final squared over 2, but remember that that's equal to GM over 2 times R plus H, and I'm sorry, there's a 2 here, right? And furthermore, this is equal to, I feel like there's something iffy strange going on here. Oh, there's no 2 there. I'm sorry. I'm just willy-nilly throwing stuff in. There's no 2 there. That's potential energy. So GMM 2R plus H is equal to minus GMM R plus H plus GMM over R. And now let's move this over, and we see that we get 1/2 plus 1. So we get 3/2 GMM R plus H is equal to GMM over R. So we can kill those. And what we see is we get that 3R to the half is equal to R plus H. Cancel this stuff out and multiply, multiply, cross multiply. So if I move this over, I get that R to the half is equal to H. Pretty simple. Long, long explanation to basically say that the change in potential energy, this is the final potential energy of gravity, this is the initial potential energy of gravity. To say this, in this problem, they're asking you how much energy do you need to put in to change the kinetic energy? How much energy do you need to put in to change the potential energy? And then they want to know what H would be if those two things are equal, okay? So I hope that all made sense. There's a second part to the problem, which in greater, or for greater heights, when you go up, when H is greater than this H, which is greater, the energy for lifting or the energy for orbiting, okay? And so we can see that if we look at it, the change in kinetic energy is mv squared over 2, which was gmm over 2r plus h. And the change in potential energy, right, was gmm over r plus h with a minus sign plus gmm over r, right? Now, as we go up, eventually, this gets less and less and less and less. The change in potential energy becomes less and less and less, right? Until it eventually just becomes GMM over R. But it's always GMM over R. But for really big H's, so for really big H's, this whole term goes away, but we're still left with GMM over R. So essentially this goes to 0. And this goes to 0. So for very far away distances, the change in potential energy is where all the energy, all the work has to be done. All the work has to be done to change the potential energy, not the kinetic energy. That's what it's basically asking you, is for greater heights, which is greater, the energy for lifting or for the kinetic energy of orbit. So for really great heights, are you going to have to put in more energy in the kinetic part or more energy in the lifting part? And since the potential energy change is always for very great heights, GMM over R, if we go back and look, the change in potential energy becomes at very great H, GMM over R, and the energy required for kinetic energy becomes 0. Therefore, eventually, at great heights, the potential energy change is always greater than the kinetic energy change. Okay, that's it. Good luck on your homework. Hope this is helpful. Sorry this last question is kind of rambling. It's difficult, and that's what I want you to see. But remember that the overall takeaway was we can just find the change in potential energy, and as potential energy final minus potential energy initial, and the change in kinetic energy, and they will be equal to our work, right? Our work is the change in potential energy. Our work is the change in kinetic energy. Okay. Anyway, good luck. Stay healthy. I'll talk to you later.